So, hi, my name is Pascal Hogan. I'm from Laval University, and I'm going to talk about femtosecond fiber lasers. Last summer, I had the opportunity to work with Mr. Michel Bichet from Laval University. He's an expert in lasers and their application to different domains. Our research group has interest in laser technology, such as ultra-short laser pulse generation, but also in all sort of other topics, such as high-resolution imaging and optical fibers. Our laboratories are located in Quebec City. So, as I said before, we'll be talking about femtosecond fiber lasers, specifically on the design of such cavities with a high repetition rate. First, I will place the project in context. Then I will introduce two nonlinear optics concepts, which are omnipresent when we have to deal with such cavities. Finally, I will present the experimental setup and conclude with some results. So let's start with the context. Am I talking strong enough?
Yes.
So we wanted to design a laser that could be used, among other things, for terahertz wave generation. There are several processes that give rise to terahertz pulses. Some of them, like optical rectification, use ultra-short pulses of the order of the femtosecond. There already exist lasers that are suitable for the task, but they are expensive and have several disadvantages. We chose fiber lasers because of their attractive properties. For example, since almost everything occurs in fiber, the beam is confined in the core where there is high intensity and strong nonlinear effect. We gave ourselves three objectives. First, we wanted to have a mean power of at least 100 milliwatts. We wanted a repetition rate of 80 megahertz with only one pulse circulating in the cavity at a time. And we wanted a duration of a maximum of 100 femtosecond. The generation of terahertz pulses have grown in interest in the last years because of the large variety of their applications. For example, the most textile or transparent to that part of the electromagnetic spectrum. So, since they have no ionizing effect, terahertz radiation have non-invasive and non-destructive way to detect weapon or potentially harmful objects. Let's continue with the theory. First, I'd like to talk about a completely nonlinear effect called self-phase modulation, or SPM. This phenomenon arises from the nonlinear refractive index. We often consider that the refractive index depends on the frequency, which is the chromatic dispersion, but in reality, the refractive index also depends on the intensity of the electromagnetic field, as you can see in this equation, where N is the refractive index, E is the electromagnetic field, and N2 is the nonlinear index coefficient. So what this equation tells us is that the refractive index should change along the fiber depending on the electric field. It has several consequences. For example, if you try to evaluate the phase shift that comes from the propagation of a distance on a distance L, you will end up with the following results. This means that the phase shift on the distance L depends on will change along the pulse. Consequently, if you evaluate the instantaneous frequency, you will find that it diverges from the central frequency as this. So this equation means that the instantaneous frequency will change along the pulse according to its shape. Also, it reveals that there should be creation of spectral components and a spectral grouping. Next, I'd like to talk about mode locking. Mode locking is a mechanism that helps us to create ultra-short pulses. In our case, we use passive mode locking, which means that there is no active components in our setup. The generate idea is that suppose you have a signal that is made of noise. It can be considered as several signals of different frequencies in a superposition. The concept is to synchronize the signals so that they all reach maximum intensity at one point. So you should have constructive interference at that point and destructive interference everywhere else. With this technique, you can create pulses of a couple of femtosecond long. I'd like to continue with materials and method. We designed a lot of fiber cavities. All of them were ring cavities, which means that instead of being reflected by mirrors, light simply follow the circular trajectory of the optical fiber again and again. We use laser diodes, such as those, for emitting at 980 nanometers as pump. The gain medium was erbium doped fiber. It is a 3-level gain medium that usually emits in the far infrared at 1550 nanometers, which is also the wavelength at which the losses are minimum in the silicon fiber. So here we have the setup for mode locking. What happens is that light comes from the right side, light comes from the right connector. It passes through a quarter wave plate, which transforms the polarization into an elliptical one. The elliptical polarization rotates when propagating into the fiber because it is nonlinear medium. And then when it passes through the polarizer, the polarizer eliminates the signal that crosses axis. There's also a half-wave plate that is used to change the angular position of all the ellipses of polarization so that we can favor ellipses corresponding to higher power. This system is called PEPM system, or nonlinear polarization mutation. And finally, the results. Here you have a schematic representation of one of our cavities. The light arrives in the WDM coupler and is reflected backward in the gain medium. The rectangle on the right is corresponds to the PEPM system that you can see here. And the third component is an isolator. It's a non-reciprocal component that forces light to circulate into only one direction. So with that kind of cavity, we obtain the following results. Here you can see the spectral bandwidth, the power, the mean power, and the duration of the pulses. Our proceed is that once the laser was mode locked, we started to change the length of the fiber in the cavity so we can adjust the global dispersion of the cavity and change the mode. You can see that we managed to attain a sufficient repetition rate of 80 MHz with 99 femtosecond pulses. However, the mean power is really insufficient. This comes from the free space propagation in the PEPM system. In consequence, Consequently, we decided to build all fiber cavities. This is done by replacing the pieces of the PAPM system. We replaced the polarizer by fiber polarizer and fiber coupler, and we replaced the retarders by polarization controllers, such as those. Who do exactly the same work. So we obtained that kind of cavity, an all-fiber cavity. We obtained our most effective results with coupler 1090 at the end. Here you have the results for that all-fiber cavity. These results are really more satisfying than the first one, and we didn't measure the duration of each in each case, but as a rule of thumb, we consider that a pulse with a duration of 100 femtosecond should have a spectral bandwidth of about 30 or 40 nanometers large. Seeing those results, we decided to try to amplify the output, then up to 100 milliwatt with a fiber amplifier. This was not really concurrent. We realized that we weren't able to increase the power to more than 60 milliwatt, and this is where the project still is today.